In this video, we continue with chapter 4.6 examples, and we are going to be looking at the definition of the rank of a matrix. So let's start with theorem 4.15. So this tells us the row space and the column space for a matrix have the same dimension. So if A is an m by n matrix, then the row space and the column space of A have the same dimensions. So here's our proof. The dimension of the row space and the dimension of the column space are both equal to the number of pivots in the row echelon form or in the reduced row echelon form of A. So if you think to the pivots, we think about that corresponds with the dimension when the matrix is in row echelon form. The first of the non-zero entries in each row, that's our pivot. So if we've got two matrices that are in row echelon form and they're row equivalent, their pivots are in the same place. So if we look back at our earlier example, we had these two matrices that were in row echelon form. The first one is just in row echelon form. So the pivots here are these first non-zero entries of each row. So in the row echelon form, we've got the ones on the diagonals in the first two rows, and in the reduced row echelon form, they are in the same position. So the pivots are in the same place regardless of whether we're in row echelon form or reduced row echelon form. So our proof here for theorem 4.15 is saying the number of pivots is equal to the dimension of the row space and the dimension of the column space. And that's going to be the same dimension for a matrix. So if we look back at that example, there were two pivots here. So that is the dimension of this matrix here. And that makes sense because we had all zeros when we reduced the form of the matrix to the bottom. The bottom was all zeros down here. So it makes sense we only had two bases here, so the dimension is 2. So the rank is known as R, that's the rank of a matrix, and it's the dimension of the row space, the dimension of the column space, and the number of pivots in the row echelon form. So that example we were looking at, this matrix here has rank R, which is 2 for this matrix because it had 2 pivots, whether we're looking at the row echelon form or the reduced row echelon form. So we're going to take a look at finding the rank of a matrix in this example. The first step is to convert the matrix to row echelon form. If you're using simply, just go ahead and go to reduced row echelon form, make life a little easier for yourself. And so if we look here at matrix A, when it gets converted to matrix B, the row echelon form, we can count here what are the non-zero rows with pivots in them. And there are 3 pivots here. And so the rank of A is 3. Essentially, you can think about it as counting the non-zero rows when you're finding the rank of a matrix. So theorem 4.16 is about how we find solutions to homogeneous equations. So if A is an m by n matrix, then the set of all solutions to the homogeneous system of linear equations AX equals 0, so remember homogeneous is when we set our equation here equal to 0, is a subspace of Rn called the null space of A, and it's denoted by n of A, like a function. So we define the null space of A to be all the x's in Rn such that A multiplied by x, where x is a vector, gives us a 0 vector. And the dimension of the null space is called the nullity of A. The null space of A is also known as the solution space of this system AX equals 0. So those terms are used interchangeably, the null space or the solution space. So let's take a look at the proof. The size of A is a m by n matrix, so you know that x has size n by 1 because we're treating x as a vector here. And so you can think about it as a row vector or column vector. So here we're thinking about it as a column vector, so it's got n rows and just 1 column. And the set of all solutions of the system is a subset of Rn. So this set is clearly non-empty because we know if you've got the 0 vector, then A times the 0 vector equals 0. So we just have to verify that it's a subspace by showing that it's closed under the operations of addition and scalar multiplication. So we're going to let x1 and x2 here be two solution vectors of the system ax equals 0. And we're going to let c be a scalar. So both ax1 equals 0 and ax2 equals 0, because those are both vectors that are solution vectors. So you know that you could pull the a out and have a of x1 plus x2 equals a times x1 plus a times x2, where these are vectors. And so that's just going to be the 0 vector plus the 0 vector equals 0. So by our matrix property that we can pull the matrix out front, and we know the addition closure holds. And then when we think about scalar multiplication, we take matrix A and multiply it by the scalar C times our vector x1. And we know we can pull the scalar out front, so that becomes scalar C times matrix A times vector x1. And we know ax1 is 0, so this is just scalar C times the 0 vector, or the 0 vector here. So that gives us closure under scalar multiplication. So both vectors x1 plus x2 and scalar C times vector x1 are solutions of ax equals 0, and you can conclude that the set of all solutions forms a subspace of Rn. So let's take a look at an example. We are going to find a basis for the null space of this matrix A here. So the very first thing we do is find the reduced row echelon form of the matrix, and then we're augmenting it with the 0 vector here. So we've used this format, R, for reduced row echelon form, and then we're attaching the 0. So we put that bar in our notation and attach it. You can say this is that we're augmenting with the 0 vector. And so that last column here of our augmented matrix corresponds with the 0 vector, and that's because we're solving ax equals 0. And x is a vector, so if you want to put the vector symbols above x and 0 when you're writing by hand, that's fine. It's also not necessary. Okay, so now we need to solve the system. Here's our pivots. And so if we multiply by x1 through x5 values, then we get this equivalent system here with this equations, our system of equations to solve. So notice already it looks like we've got some free variables here, because notice that we get 0 equals 0 down here in the last row. So we know right away that x5 is going to be a free variable, and then it's also looking like x3 is going to be a free variable as well, because it's showing up in these two spots. All right, so our two free non-pivot variables are x3 and x5. If you look back at our pivot rows, you can see the pivots correspond with x1, x2, and x4. That's another way to see the free variables. So we are going to choose parameters x3 equals s and x5 equals t. You can call them the other way around as well. And we're going to solve then for our pivot variables x1, x2, and x4 using back substitution. So in this system here, I've plugged in s and t's in place of x3 and x5. So if we solve, we can see, okay, x4 is going to equal 2t, just isolating x4. X2, if we bump these over to the other side, we get from here, x2 equals s minus 2t. So all we're doing is taking these values and isolating x2 by moving those to the other side. And then similarly, x1 is going to be negative 3s plus 4t just by moving these values to the other side. So that means that n of a, the null space of A, is the set of all vectors in this form, where x1 is negative 3s plus 4t, And x2 is s minus 2t. And s is just going to be s. X4 is 2t, and x5 is just going to be t. So when I said s is s, I could have said x3 is s and x5 is t. All right, so then when we form our basis, we can pull out the s and the t, and the basis is the two vectors associated with the coefficients for s and t. So our basis here for the null space of A is the column vectors -3, 1, 1, 0, 0, and the column vector 4, -2, 0, 2, and 1. Okay, so just to recap our process here, our first step to finding the basis for the null space was to augment our reduced row echelon form of the matrix with zeros here. Then we found the pivot columns and multiplied through by our x1 through x5s to set up the system of equations. And then we proceeded like we have earlier. We went ahead and realized that x3 and x5 were free variables, so we called those s and t. And then we just solved the system in terms of s and t. And then what we did for our last step over here was to pull out the s and t and then figure out what are the vectors that form the basis for this null space. So theorem 4.17 is about the dimension of the solution space. So if A is an m by n matrix of rank R, then the dimension of the solution space of AX equals 0 is n minus R. So the n, remember, is the dimension and R is the rank. So the difference between the dimension and the rank is the dimension of the solution space. So if you come back here, so our previous example, this matrix had 3 pivots, so it had rank 3. It had 5 dimensions because it was a 5 by 5 matrix here. And so the 5 dimensions minus the 3 pivots is 2. And we see that there were s and t as the 2 free variables, and we had 2 vectors as the basis for our null space. So that dimension of our solution space was 5 minus 3, or 2 in the earlier example. Another way you can think about this is that the dimension of the whole system equals the rank of A plus the nullity of A, where, remember, nullity of A is what we call the dimension of the null space. So let's take a look at the proof. So just to verify, in our earlier example, we had 5 dimensions because we had a 5 by 5 matrix, and its rank was 3, and the dimension of the null space was 2. Okay, so A has rank R, so you know that it's row equivalent to a reduced row echelon matrix B with R non-zero rows, or you can think about those as R pivots. No generality is lost by assuming that the upper left corner of B has the form of the R by R identity matrix. What that's saying is we just put them all together in the upper corner. If you look at this example we were looking at earlier, the pivots were for x1, x2, and x4, but if we rearrange things, we're not going to lose any assumption power here. So that's what we mean when we say without loss of generality. You could rearrange and have the identity matrix for R spread out, or you could rearrange it and put it in the upper left corner here as we are. Okay, moreover, the 0 rows of B contribute nothing to the solution, so we can discard those to form the R by N matrix B with the apostrophe, where B apostrophe is the augmented matrix that is the identity matrix with C augmented to it. So this matrix C has n minus R columns corresponding to the variables xr plus 1, xr plus 2, and so on. And the solution space of AX equals 0 can be represented by this system here. So we've got here R rows that correspond with the rank of the matrix. And then after that, you've got these extra columns that form the dimension. And so these columns are corresponding to these variables xr plus 1, xr plus 2, xn. And so that's going to be how we find the solution space. So this is going to correspond with the free variables. So solving for the first r variables in terms of the last n minus r variables produces n minus r vectors, right? That's going to correspond in here, just like in this example, we had 2 vectors because our rank was 3, and we had 2 free variables. And so the solution space has dimension n minus r. I think it's easier to see from our earlier example. So we saw here we had the 3 pivots, and then you have these leftover columns. This is what they're talking about when they say n minus r. So in this case, our n is 5, our rank is 3, so n minus r are these 2 leftover columns that ended up associated over here with our free variables that form the basis for the null space. So the nullity, the dimension of the null space, is 2. So let's take a look at an example here. So we are going to let the column vectors of matrix A be denoted A1, A2, A3, A4, and A5. And so we're first going to find the rank and the nullity of A, and then we're second, in part B, going to find the subset of the column vectors of A that form the basis for the column space of A. So here we've got matrix A. Notice we've labeled the column vectors A1 through A5. And so we're going to move to B, the reduced row echelon form of the matrix. So that's over here. And you can verify it's reduced row echelon form because every column with 1 in the leading coefficient, our pivot columns here, have zeros in every other position of the column. All right, so B has 3 non-zero rows. So the rank of A is 3. And we're looking at B because it's a reduced row echelon form of A, but we're still able to generalize back to A when we say rank of A is 3. So we'll say R equals 3 for A. That's our rank. And the number of columns of A is 5. So n equals 5 is our dimension of A. And that's because it was, is it a 4 by 5 matrix? M by n. So the nullity of A is going to be 5 minus 3 or 2. So nullity is going to equal all right, so the next thing to do is to find the subset of the column vectors of A that form the basis. So we know from the row echelon form that the first, second, and fourth columns of B are linearly independent. Those are our pivot row column, or our columns with the pivots in them. So the corresponding vectors with those rows are going to be the basis for the column space of A. And here, these values are going back to the original A. So these are coming from matrix A. So because those are the linearly independent vectors, they form the basis for the column space because we're looking here at column space. Okay, in the next video, we're going to take a look at solving systems of linear equations.